Hey guys, what's up? I hope everybody's having a good day so far. Hopefully you've had a good week, making all the adjustments, trying to get your head straight. Hopefully it's getting a little easier. I just want to say thanks for being so flexible. This has just been crazy, and just trying to get everything organized has been a trip for sure. So hopefully things are settling down. You're kind of getting into a little bit of a routine here, and we can make some progress. Really start focusing on what we're trying to learn here, see what we can do. So today we're going to look at Bernoulli differential equations and a general substitution method. So last time we finished off with what we called a homogeneous equation, and we made a substitution y equals u times x. Today we're going to have a different differential equation. It's called Bernoulli's differential equation, and we're going to make a different substitution. So everything here in this section is really just a substitution to turn the differential equation into something that we can solve. So let's look at the definition of a Bernoulli differential equation. So definition. The differential equation dy dx plus p of xy equal to f of x y to the n is called a Bernoulli differential equation. So the volume, let me see. Equation. Yeah, the volume, just make sure your volume's up on your computer, or just make sure your volume's up, whatever you're using. If you have headphones or something like that, there's like another volume switch, just double check. I have it on my computer. I have two computers going here, one for the chat and one for the writing, and I can hear it on the one where I have the chat going. So just double check, make sure everything's good. So yeah, that's a Bernoulli differential equation. And for n equals 0 and n equals 1, it's a linear equation. So if n equals 0, it's separable. If n equals 1, it's a linear equation, possibly still separable, I guess. So yeah, this is a nonlinear equation. So note, it's a nonlinear equation because of this y to the n power right here. So to solve, well, let's just make a note here. Like I said, note for n equals 0 and n equals 1, this is a linear equation, possibly separable. So just use the methods that we already know for separable and linear equations. Now, to solve, we make a substitution. So everything in 2.5, in this section, we're going to make a substitution. Last time we made a substitution. Good. Yeah, I have my microphone set up that I use for my YouTube channel, and just trying to make the quality a little bit better. So yeah, I think my gain may have been up too high last time, so I tried to tweak it a little bit. Hopefully this is going to go a lot more smoothly than what we were doing before. The recording just processed on some of my other classes from Monday, so it's just too long for processing. So hopefully these YouTube videos will be able to process pretty quickly. Both of mine from yesterday process quickly, so should be a better option overall, I think, if you have the ability, I guess. So let's look at the substitution. We make a substitution here. U equals y to the 1 minus n. So we make this substitution, u equals y to the 1 minus n. So then, whoops, misspelled substitution up here. Oh well, I'll fix it later. So if we make this substitution, which will reduce the Bernoulli differential equation to a linear equation in U. So U becomes the new dependent variable. So U is the new dependent variable. So U is the new dependent variable. So note if U is equal to y to the 1 minus n, then y is equal to, if you solve for y, I would need to say that that's going to be u to the 1 over 1 minus n. So basically need to raise both sides to the 1 over 1 minus n power. And then dy dx be equal to 1 over 1 minus n times u to the 1 over 1 minus n minus 1 times du dx. So that's just like a chain rule differentiation to substitute in what the differential dy dx would be. So we can simplify this to 1 over 1 minus n u to the 1 minus 1 minus n over 1 minus n du dx. Which is equal to 1 over 1 minus n u to the, let's see, that's going to be n over 1 minus n, and then du dx. So make the substitution into the differential equation now. So this is dy dx. And so that's what we're going to substitute in for dy dx. And now wherever we see y, we're going to substitute in this u to the 1 over 1 minus n. So this is going to tell us our Bernoulli equation becomes 1 over 1 minus n u to the n over 1 minus n du dx plus p of x times y, but y is u to the 1 over 1 minus n equals f of x times u to the 1 over 1 minus n to the nth power, because that's y to the nth power. So now basically we're subbing everything into differential equation. So the differential dy dx is right here. So basically this right here is dy dx. This right here is y, and this right here is y to the n. I'm just replacing it with what it is in terms of u. And now we're going to do a little bit of algebra to show that we have a linear equation in terms of u. So this is going to be, let's multiply everything divide everything by this term right here. So divide through by u to the n over 1 minus n. And multiply by 1 minus n. So that's going to be du dx plus 1 minus n p of x and then u to the 1 over 1 minus n over u to the n over 1 minus n equals 1 minus n f of x. And this stays the same. So this is going to be du dx plus 1 minus n p of x, and then u to the 1 over 1 minus n over 1 minus n equals 1 minus n f of x. And this right here is just going to be 1. Notice you have 1 minus n over 1 minus n. So this is just going to be 1. And it is now a linear equation in terms of u. So du dx plus 1 minus n p of x, u to the first power equals 1 minus n f of x. So that's our Bernoulli equation after we make the substitution. So this is what happens every time you have a Bernoulli equation and you make the substitution. So this is always the new differential equation to be solved after making u equal to y to the 1 minus n, where n comes from the original differential equation. It's the nonlinear exponent. Well, possibly linear, but most of the time it's like n equals 2, 3, 1/2, 3/2, something like that. It could be anything. But this is the general approach. So it's pretty straightforward, actually. If you would just want to memorize this equation right here, the only thing that changes is really you just stick a 1 minus n right here and a 1 minus n right here. And just remember that u is y to the 1 minus n. So let's look at an example. So example, solve differential equation x dy dx minus 1 plus x y equals x y squared. So this is a first order nonlinear non-separable equation. It's a Bernoulli equation because we see this term right here. So that's our n for our Bernoulli equation. So it's nonlinear, it's non-separable. We have to try something else, and we see that square term, so that hints to us that it's Bernoulli. However, first thing we have to do is put it in standard form. So first, put the dE in standard form. And how do we put a differential equation in standard form? We divide by the leading coefficient. So then that would mean we get dy dx minus 1 plus x over x y equals y squared. So we're going to make the substitution u equals 1 minus 2, or sorry, y to the 1 minus 2, which is y to the negative 1, which is 1 over y. So that's basically the substitution we're making. Oh yeah, sorry, I'll try to be more careful. Let's see. I think you should see it if I get it close enough. Sorry about that. I don't know, we'll see. I'll just double check. Maybe there's a way I can highlight where my pen is. I'll figure that out at some point. So u equals 1 over y basically is a substitution we're going to make. And we know now that the differential equation is going to become du dx minus 1 minus n 1 plus x over x times u equals, see, f of x here is just 1, so 1 minus n times 1. Because f of x equals 1, p of x is this thing right here. So this is our differential equation that we need to solve. And n equals 2, so this du dx minus 1 minus 2, 1 plus x over x times u equals 1 minus 2. And now we have a linear differential equation du dx. 1 minus 2 is negative 1, so plus 1 plus x over x times u equals negative 1. So it's a nice linear differential equation. Now we use the integrating factor to solve. So now use integrating factor to solve. So the integrating factor is going to be e to the integral p of x dx. And where is p of x? It's right here. So that's our p of x. So let's do that integral. That's going to be e to the integral 1 over x plus 1 dx. Just doing a little algebra before we integrate. So it's going to be e to the natural log x plus x, which is going to be x e to the x. Well, let me not skip that step. That's going to be e to the natural log x times e to the x, which is x e to the x. So that's our integrating factor. Now multiply the whole equation by the integrating factor. So now multiply the differential equation by the integrating factor. So you multiply the differential equation by the integrating factor. We get x e to the x du dx plus 1 plus x e to the x u equals negative x e to the x. And what do we know? We know on the left the product rule always becomes du dx of integrating factor times times u. So it's always integrating factor times the dependent variable, or whatever we're treating as the dependent variable. Here we're treating u as the dependent variable. On the right, it's just negative x e to the x. So now we do the integral on both sides with respect to x. So integrate with respect to x, integrate with respect to x. We're going to have integration by parts over here on the right-hand side. I'll just do a tabular integration. So put a negative x here, e to the x here, and negative 1, 0, e to the x, e to the x, plus, minus. So the x e to the x u is going to be equal to, let's see, multiply these, get negative x e to the x, minus minus is plus e to the x plus c. So we got our integral by parts. Now all we have to do is solve for u. So now solve for u. So solve for u. We get u is equal to -1 plus, let's see, the e to the x would cancel, so I get 1 over x plus c over x e to the -x. Now, that is what u is equal to, but we really want to know what is y equal to. And what was u? U was equal to 1 over y. So 1 over y is equal to -1 plus 1 over x plus c over x e to the -x. So y is equal to the reciprocal, so 1 over -1 plus 1 over x plus c over x e to the -x. And we don't have an initial condition. Actually, I probably would have solved for c earlier if I had an initial condition, but I don't have one. But yeah, that's the idea. So the easiest thing to do is just to remember after the substitution what the differential equation turns into. And that is the thing with the du dx plus 1 minus n p of x u equals 1 minus n f of x. So that's definitely the easiest thing to do. Another approach would be to literally go through, make the substitution u equals y to the 1 minus n, solve for y, find dy dx in terms of u, multiply through. It's basically the whole general process. But this one, in my opinion, unlike the integrating factor, you don't want to necessarily remember the process here. You just want to remember what it turns into as far as the differential equation. So basically, you're wanting to remember that you always get this every time. This differential equation is the new one that you want to solve. So put some stars right here. When you have a Bernoulli equation, it always turns into this new differential equation, this new linear equation. So that's my recommendation for these problems, for Bernoulli problems. So again, as always, just post questions over in the chat. I'll try to get to them as I can. So let's see if there are any questions or anything like that. I may try to pull up another example here from previous years and things like that. See what we did in the past. Just to give you an idea of maybe a problem that you might see or something like that. So just look up one here, Bernoulli problem. So let's look at an example here, one more. Let's see. Got one here, 3x dy dx minus y equals 3x e to the x y to the 4 for x greater than 0. Again, no initial condition here, so don't worry about solving for plus c. So the solution, we'll just divide, make sure it's in standard form, so put into standard form first. So put it into standard form first. So how do we put it in standard form? We divide by the leading coefficient, so that gives us dy dx minus 1 over 3x y equals e to the x y to the 4. And n is equal to 4. So we're going to make the substitution u equals y to the 1 minus 4, which is y to the -3. So that's our substitution that we're making, u equals y to the -3. Now, what is our 1 minus n? 1 minus n is equal to -3. So then the Bernoulli differential equation is going to be du dx minus negative 3 times 1 over 3x u equals negative 3 e to the x. So here's 1 minus n times p of x times u. Here's 1 minus n times f of x. So this differential equation becomes du dx plus 1 over x u equals negative 3 e to the x. So it looked really hard to begin with, but actually once we get to this linear equation, it's actually pretty straightforward, pretty easy. So it's going to be integrating factor. So integrating factor is e to the integral 1 over x dx, which is going to be e to the natural log x, which is just x. So we get x du dx plus u equals negative 3x e to the x. And again, we're just going to do an integration by parts over there. So this is going to be d by dx of x times u equals negative 3x e to the x. So we have to solve this integral. So integrate both sides with respect to x. That's going to be x times u equals, let's see, do a tabular integration here, u dv, so negative 3x e to the x, negative 3, 0, e to the x, plus minus, this is going to be negative 3x e to the x plus 3 e to the x plus c. So then that tells us that u is equal to negative 3 e to the x plus 3 over x e to the x plus c over x. But what is that? That is 1 over y cubed. So 1 over y cubed equals this thing, negative 3 e to the x plus 3 over x e to the x plus c over x. Now, it doesn't matter if you leave it this way or not, unless it says solve explicitly for y. So if possible, we want to solve explicitly for y. So y would equal, we could just say negative 3 e to the x plus 3 over x e to the x plus c over x to the negative 1/3. And that would be our answer. So it's a good one to look at. It's a good practice problem. That was on a previous exam, so just throwing that out there. It's a good one. It looks intimidating, it's really not. So we try to make them on the exam be a little easier whenever you actually work it out. So just another good example of a Bernoulli equation. So again, as always, just post your questions over in the comments. I'm keeping track of those live. I have another computer up here, so yeah. If there are no other questions or anything like that, we'll move on to one more substitution to make. Maybe when it's not homogeneous and it's not Bernoulli, what else can we do? Well, maybe it has another form and we can use a different type of substitution. So the last one is a particular type of substitution, and we'll just call it like a substitution to reduce to separable. So this is like just a general type of substitution that you could make if it's got this particular form, and it'll make it a separable equation. So it basically is going to work for a differential equation of the form dy dx equals some arbitrary function f of ax plus by plus c. So this is for any general function of the form, or differential equation of the form dy dx equals arbitrary function f of ax plus by plus c. So any differential equation of this form, we can try the substitution here. So the substitution we need to make is we let u equal ax plus by plus c. So that would be turning the right-hand side basically into f of u. Okay, yeah, EJ's got a question, said I'm confused with the sign after dy dx in the Bernoulli equation. When defining it, the sign was a plus, but during the problem we used a negative. Okay, so basically what we're saying in those examples are that right here, let's look at this example. This is part of p of x. So p of x is negative 1 over 3x. So if you were to add p of x, you would basically add negative 1 over 3x. So that negative sign is really part of the p of x in the original, like, general form right here. So px contains the negative sign because the general form, like you said, you're right, the definition is it's a positive sign. So then p of x would contain the negative sign if there is a negative sign. So even at the very beginning, p of x right here has to contain any negatives that you see. So that's a good point. But yeah, it's just part of your p of x function. Good question. Yeah, it's the same thing. The negative sign is always part of a p of x. So your p of x is the negative part. It's got the negative and the function. So in both cases, it's the same. It's the same p of x in both cases. It's just instead of writing plus negative 1 over 3x, I just write minus 1 over 3x. All right, so let's look at what happens here. So du dx will be equal to a, basically differentiate both sides with respect to x, plus b times dy dx. So for dy dx, I'm going to substitute in this thing. So dy dx will be equal to 1 over b times du dx minus a. So that will turn differential equation into 1 over b times du dx minus a equals f of u. A is a constant, so we could get du dx equals b times f of u plus a. And now it's separated. Well, I can say integral 1 over b f of u plus a du equals integral dx. This one's so simple, though, that there's no reason to memorize what it turns into. Making the substitution is generally straightforward enough. You don't have to worry about this. You just have to make sure you take the derivative du dx and figure out what it is in terms of dy dx, and then substitute in dy dx. But if you want to memorize this one right here, this is totally okay. So let's look at an example. Let's say we have dy dx equals tan squared x plus y. So here's our differential equation. Let's look at our substitution. U equals x plus y. So the solution is to let u equal x plus y. Then du dx would be 1 plus dy dx, basically differentiating both sides with respect to x. So dy dx is u prime minus 1, or du dx minus 1 equals dy dx. So we get du dx minus 1 equals tan squared of u. So du dx equals 1 plus tan squared. So du dx equals 1 plus tan squared. There should be a bell hopefully going off in your brain a little bit. What is 1 plus tan squared u? What is 1 plus tangent squared of u? Don't everybody say it at the same time. What is 1 plus tan squared of u? It's a trig identity. Hopefully it's still there somewhere. What is that trig identity? 1 plus tan squared equals, first person to type it gets 5 life points. Something with secant. That's correct. What is it though? Anybody specifically? Secant squared u, that's right. Secant squared u. So this is equal to secant squared u. So we have the differential equation. We can separate it. Du over secant squared u equals dx. And now integrate both sides. On the left with respect to u, on the right with respect to x. It's a separable equation now. So we're integrating on the left. What's 1 over secant squared? So let's, what's 1 over secant squared? First person to say the answer gets 5 more life points. Yeah, I have like a 10-second delay set up, so not sure why. It's not like anything crazy is happening here. So what's 1 over secant squared? It's cosine squared, that's right. So there's cosine squared u du equals integral of x dx, or sorry, just dx. Now, how do I integrate cosine squared? I can integrate the right, no problem. How do I integrate cosine squared? The right-hand side, x plus c, I got that. Cosine squared is what? How do you integrate that? Someone hook me up. What do we do? Somebody type a trig identity that I need to use. What is the trig identity we need to use to integrate cosine squared? The double angle formula. So that is, do you type it? It's 1/2 1 plus cosine 2u. Exactly. So now integrate, get 1/2 integral of 1 is u plus integral of cosine 2u is 1/2 sine 2u. That's right, Philip. 1/2 sine 2u equals x plus c. So it's quite involved so far. Now this is 1/2 u plus 1/4 sine of 2u equals x plus c. So that's a 4. Sorry. That's a 4. So now I substitute what u is back in terms of x and y. So basically u was equal to x plus y. So this tells us our equation. We're going to leave it implicit, of course. It's going to be 1/2 x plus y plus 1/4 sine of 2x plus 2y equals x plus c. And I'll just leave this implicit solution because solving for y will be very difficult. So this one is just an implicit solution. We're going to leave it like that. All right. I have one more example we can look at. So one more example. And the example is to solve differential equation dy dx equals x plus y plus 2 squared. And let's see, I have initial condition. No initial condition again. So solution, gonna let u equal x plus y plus 2. And then differentiate both sides with respect to x. We get du dx equals 1 plus dy dx plus 0. So dy dx is equal to du dx minus 1. So that gives us du dx minus 1 equals u squared when we substitute everything into the differential equation. So du dx minus 1 equals u squared. So move the 1 over to kind of start separating the variables. We get du dx equals 1 plus u squared. Now to separate the variables, divide both sides by 1 plus u squared. So du over 1 plus u squared equals dx. And now integrate both sides on the left with respect to u, on the right with respect to x. So what is the left, the integral? 1 over 1 plus u squared du equals x plus c. What's integral 1 over 1 plus u squared? Or sorry, antiderivative. What's antiderivative 1 over 1 plus x squared? Anybody? As fast as humanly possible. See what we can get. Don't Google it. Arctan, that's right, arctan x. Oops, it's not an x, it's a u, sorry. I made a mistake here. It's be 1 over 1 plus u squared. So it'd be arctangent of u. Arctan of u equals x plus c. And that would mean that arctan x plus y plus 2 equals x plus c. And again, implicit solution is probably okay. This one wouldn't be too bad. So let me circle this one as like an okay solution. But what we could do is we could say that x plus y plus 2 be equal to tangent x plus c, and we could solve for y as tangent x plus c minus x minus 2, and that would be an explicit solution. But just to cosine, just do, yeah, just doing explicit solution is okay. Implicit solution be okay. It really depends on the directions in the problem. So yeah, definitely I'm gonna have to turn off the delay here on the chat. So, or at least in the next time I stream. So be a little more fluid with the comments. So, but yeah, that's the last thing in the section. Really, is just making these this random, or it's not really random. It's just a general substitution for a very specific form, Ax plus By plus C, to solve a differential equation that way. Next time we'll start application problems. We'll do like a whole slew of application problems, and then probably get into some general theory for second order equations. We have, we're kind of ahead of a schedule a little bit. We're only supposed to be starting this section today. So we're a little bit ahead of schedule, so that's good. But don't want to slow down too much, just to make sure that we have plenty of time later on to cover everything that we need to cover. So I'm not going to rush too far forward, but I'm not going to slow down too much either. So good examples here today, good discussion. Yeah, so any questions before we get done here? I'll email you some updates about exams and things like that. So just stay tuned. So just waiting for some questions. If not, feel free to head out. And we'll meet back again next week. Another live stream on Tuesday. Yeah, the test assignment is really just like a test, not a exam. It's a test for me to get you guys to do something. I'll send you an email more. Yeah, I'll send you an email about details about what to do with that. Yeah, so yeah, writing on a tablet definitely is like definitely a little bit different. But here on YouTube, at least you can like pause and rewind and do all that live. So yeah, doing it on the tablet, I can definitely like write a lot faster. I'm not having to walk back and forth in the room. So yeah, it's definitely easy to go too fast. That's why I'm slowing down here. I'm going to stop. So yeah, you can always rewind. Is web work going to be as hard as we get with problems so far? It is killing me. Yeah, web work is good. Like it's pretty tough, but like the homework is tough, but also have some like extra examples online for like videos that you can watch, and they're a little tougher too. At least the past couple of linear equations. The last one was pretty tough as well. So if you can do all the tough stuff, you should have no problem. Yeah. Yeah, so just do the problems on WebWork, do the book problems. Those are always like good resources. That's like the number one thing to do is both of those. And then you can you should be prepared. Don't get overfit basically to one type of like problem. Don't get overfit to WebWork, or don't get overfit to book problems, or don't get overfit to exams that you have from previous years or whatever. Like that always messes people up. But just have a good general overall like robust understanding of the material. That way you can handle anything that comes your way. So that's what I always tell my students. So yeah, just hang in there. Should be good. Some of the homework problems do get a little difficult in chapter 4 and chapter 6, so they get a little tedious. I mean, at least you're not doing surface integrals, right? So that's what everybody is always like, at least it's not surface integrals. But some people like surface integrals, so it's just my take on it. I like surface integrals, now that I kind of understand them a little bit. But when I was in your shoes, for sure, I was like, I don't know what's really going on too much. I can maybe do it, but yeah, I didn't really understand. So differential equations just seem to be easier to understand what's going on. You're basically trying to find a function that satisfies the equation. So yeah, I'll try to slow down. I'll try to reduce the delay. That way we can have a more fluid conversation. So try to slow down as in like, yeah, just not blow you away so quickly that you don't have to rewind so much, you know. Won't write more slowly or talk more slowly, but just, I don't know, try to give you a little time. So anything else? Okay, if there's nothing else, I'll send you an update, an email, try to keep you updated on what to do with that little thing on Moodle. And yeah, just stay tuned. Thanks for being flexible and working with us. And hopefully this experience is going to be a lot better than you thought it was going to be. So trying to do everything I can to help make this as painless as possible. So I'll see you guys next time. Have a good weekend if I don't hear from you. Talk to you later.